Okay, next up is question 5, which says, use the fact that f of x, which is equal to 1 over 1 minus x, is equal to 1 plus x squared plus x cubed, and so on, which note this can be written using sigma notation as the sum of x to the n, where n starts at 0, and here x is strictly less than 1 in absolute value, to derive the Maclaurian series for the following functions. Find the interval and radius of convergence for each series. All right, now I've taken the wording of this question directly from my math lab, and here's what these instructions are really telling you. Okay, so first recall our result on geometric series that says that the sum a plus ar squared plus ar cubed and so on is equal to the first term of the series, that's a, divided by 1 minus the common ratio r. And we have equality here provided the common ratio r is strictly less than 1 in absolute value. Okay, so now for this result that they quote in the instructions, this is really just a special case of this more general result on geometric series. Okay, so note that if I set a equal to 1, that's the numerator, and r equal to x, that's right here, okay, this result says that 1 over 1 minus x is equal to a, which is 1, plus ar, that's 1x, which is just x, plus ar squared, that's 1x squared, that's just x squared, and then x cubed, and so on. And we'll have equality here provided the common ratio, which is x, is strictly less than 1 in absolute value. Okay, so that's where they're getting this. Okay, and in any event, let's go ahead now and tackle part A. The big idea is to recognize the expression for the given function as something of this form, a over 1 minus r, and then we're going to apply this result. Okay, so here, g of x is 1, so that's going to be my a, over 1, and see, since I have a plus 2x squared, I can write that as minus a negative 2x squared, and so here, the common ratio r is negative 2x squared. See, now I can expand this expression into a series using this result. Okay, so here we have a, which is 1, and then to get to the next term, multiply by the common ratio r, which is negative 2x squared. So that gives us 1 minus 2x squared, multiply again to get plus 4x to the 4th, multiply again to get minus 8x to the 6th, so on and so forth, and we'll have equality here provided the common ratio r, which again is negative 2x squared, is strictly less than 1 in absolute value. All right, cool. So now note that this condition on x can be rewritten in the following way. So first, I can take the negative 2 out of the absolute value and drop the negative, divide both sides by 2, and so the absolute value of x squared is strictly less than a half, and then taking square roots of both sides gives me that x in absolute value is strictly less than the root of a half. Okay, now for this series, I've just copied it down here without all the clutter. And so what we have here is that g of x is equal to 1 minus 2x squared plus 4x to the 4th minus 8x to the 6th, and so on, provided x is strictly less than the root of a half in absolute value. Okay. Next, note that the series here is centered at a equals 0, right? We're just looking at powers of x. And so this is the Maclaurian series for our function g of x. All right, so now let's go ahead and look at a graph real quick to help us visualize this. Here is our g of x function. And then these dashed vertical lines, these are the bounds on x, right? Saying that x in absolute value is strictly less than the root of a half is equivalent to saying that x is strictly greater than negative root of a half and strictly less than positive root of a half. Okay, so I'll go ahead and plot the first few polynomials. So there's our p0 based at a equals 0. There's our p2, that'd be our quadratic approximation. These are the first two non-zero terms of the series. Then the first three non-zero terms, right, that's up to degree 4, so this is p4 of x, and then p6, because here I'm going out to the degree 6 term, so on and so forth. So we can see as n increases, I'm getting better and better approximations. Now here I'll take these out so it's a little less messy. Let's go ahead and plot polynomials to even higher degrees. Okay, so here I'm going to just increase n, and I can see, right, I'm getting better and better approximations. But also note, right, that the approximations appear to be breaking down, okay, near these vertical lines. Okay, or put another way, right, we're getting convergence on this interval where x is strictly less than the root of a half in absolute value, but outside that interval, okay, the approximations break down. Okay, so we get convergence to our function g of x on this interval. All right, very good. Now, this is what I'll call the expanded form of the Maclaurian series, but I can also write this series using sigma notation. Okay, so to do that, note that since I have an alternation in sign, if I start the index n at 0, I need a -1 to the n. Okay, then note for the coefficients I have these powers of 2, right? So 1 is 2 to the 0 power, then 2 to the first, 2 squared, 2 cubed, and so on. So I need a 2 to the n. And then for the powers of x, well, these are going up by 2, right? So 0, 2, 4, 6, 8, and so on. So I need an x to the 2n. All right, so lastly, the interval and radius of convergence for this series. Well, we've essentially already stated these, but I'll go ahead and make it a bit more explicit. So the interval of convergence is right here in blue, right? And that comes just from this statement right here, that the absolute value of x is strictly less than the root of a half. Okay, so the radius of convergence, remember that's just the gap between the center of the series, which is at a equals 0, and either one of these endpoints. And so here, r is equal to the root of a half. All right, very good. So let's go ahead now and look at part B. Make a little space here for us. All right, here's part B. And so we have that h of x is x over 1 plus 2x squared. And note first that h of x is x times 1 over 1 plus 2x squared. And this is just g of x. So put another way, h of x is simply x times g of x. And see, now we can use our work from part A to expand g of x into its Maclaurian series. Okay, and here, right, we have that g of x is equal to this series for x strictly less than the root of a half in absolute value. And now what I'm going to do is I'm going to go ahead and distribute that x. Okay, so this is going to give me x minus 2x cubed plus 4x to the 5th minus 8x to the 7th, and so on. Okay, and note that if I multiply a series by x to any power, okay, so in this case I'm just multiplying by x, but more generally, if I multiply it by x to the m, where here m is some positive exponent, okay, this will not affect the interval of convergence. Okay, so here we have the expanded form of the Maclaurian series, because again, this series is centered at 0, of our function h of x. Okay, I can write that in sigma form. Okay, note that this looks exactly like the sigma form for g of x. The only difference is the exponent on x, right? And for g of x, we had x to the 2k. And since for h of x, we're just multiplying the series for g by x, okay, this is just going to bump up that exponent to 2k plus 1. And so there we have the sigma form, and then, right, since multiplying by x does not affect the interval of convergence, all of this is the same as it was for g of x. Okay, now to finish, let's go ahead and look at a graph here. So here we have our curve for h of x, right? We're looking at the series centered at a equals 0, and here are those bounds on x again. So I'll go ahead and plot the first couple polynomials, and again we see that we're getting convergence to h of x on this interval, right? Outside that interval, right, the convergence breaks down. All right, great. Well, that's a good place to stop. I will see you in the next video.